everybody, welcome back to Fundamentals of Physical Geography. In these next few sessions we're looking at a topic that's right at the heart of physical geography: energy and materials in the Earth's surface environment. Energy drives the processes. The materials are what the physical environment around us, the landforms and the landscapes, is what they're made of. We're going to be looking at the interactions between the energy and the materials driving processes and creating landforms, landscapes, and the physical geography that's all around us. Now, you've seen my sketch before of the basics of physical geography. We have an Earth's surface, we have the near surface environment with the atmosphere and the substrate. What we're focusing on right now is the energy that's coming into that environment. So, for example, we have solar energy affecting the surface, driving the hydrological cycle, for example. We have Earth interior energy driving plate tectonics and volcanic activity. And we have the Earth's gravity pulling through the surface, and a major driving force in a lot of geomorphology, a lot of landforms and landscape processes which involve things being driven downhill from one location to another: sediment transfer, erosion, transport, deposition. Everything at the heart of geomorphology is driven by gravity, solar energy and Earth interior energy. So that's what we're going to be looking at over these next few sessions. We can think of physical geography as being focused around this interaction between energy and materials. So energy, over the course of time, things don't happen instantaneously, over the course of time, energy acts on materials at the Earth's surface. That interaction of energy and materials drives processes. I mentioned plate tectonics, erosion, transport, sediment transfer, deposition, all these different processes, weathering, all the things that you think of as being at the heart of physical geography stuff going on. Well, they're driven by this interaction of solar, Earth interior, gravitational energy on materials driving all these processes. Over the course of time, those processes lead to the forms or features, landforms, landscapes. And it leads to the distributions, the geographical variations, the geography in those features. Now, those forms, distributions, geographies, landforms, landscapes, they have an impact on the way that energy affects the materials. The processes have an impact on the materials. So we're not talking just about a line going from energy at one end to physical geography coming out at the other end. It's a circular process: energy, materials, processes, forms, geography, time, circulating, cycling. We're going to be talking about a lot of different cycles in physical geography. Physical geography is itself a cyclic process. Now, what I'm saying there might remind you a little bit of what we said about W.M. Davis and the geographical cycle earlier on in the course. Let's just tie those two things together a little bit. So you remember W.M. Davis and his cycle of erosion, or the geographical cycle, and we can reduce the geographical cycle to the idea that landforms or landscapes are the result of, or the outcome of, structure, which might be pre-existing landforms, might be geological structures, plus processes acting on them over the course of time. Structure, process and time, according to Davis, generate landforms. Now, in Davis's model, or modern interpretations of Davis's model, the structure, the process and the start of his whole cycle is based on uplift, resulting from Earth interior energy, tectonic activity, we would now recognise it. And long-term denudation of the landscape is driven by solar energy, gravitational energy, energies driving those denudational geomorphic processes. So in all of that, to us, in a modern interpretation relies upon the energy that we're going to be starting to talk about in this session, acting upon the materials that underpin everything that's happening at and close to the Earth's surface. So energy and materials is a really important central point in understanding physical geography and the development of landscapes around us. That's what we're going to be looking at over the next few videos and in the online resources that I'll be providing for you. Now, don't forget that the sessions we're working through at the moment are all connected together. So what we're talking about now in our session on energy and materials and leading on to thinking about landforms is very strongly connected back to the earlier sessions. For example, the session that we had on Earth's astronomical context, where we were saying how much of Earth's physical geography is actually dependent on its position as a planet in space and its relationship, for example, to the Sun. Remember back to those sessions now as we're talking about solar energy impacting the Earth's surface. One point in particular that I wanted to make was about the units we're going to be using. I'm going to be talking later on in the session about energy coming in at watts per metre squared. Well, watts, I'm sure you're familiar with, that's the power of a light bulb, for example. You'll be familiar with a 60 watt or a 100 watt light bulb. So why are we saying watts per metre squared? Well, even on my phone I can set my torch off and it's generating a certain amount of light. If I put that close to the surface, that light, the wattage if you like, which is coming out from that light, is being concentrated over a small area, so it's quite bright, it's quite intense over that small area. If I spread it over a larger area, it becomes less bright, less intense. So it isn't just the wattage that I'm interested in when I'm thinking about the impact on a surface, it's the watts per metre squared or per centimetre squared. It's the watts over a given unit area. So likewise, when we're talking about solar energy affecting the Earth, we're not just talking about how many watts the Sun is emitting, although we are interested in that. We're also interested in how concentrated that wattage is at different parts of the Earth's surface. So how many watts per square metre arriving at the equator, or arriving at 53 degrees north, or arriving at the North Pole or the South Pole. So watts per metre squared is what we're going to be talking about in terms of the energy input, both from solar energy and also from Earth interior energy, when we come on to say a little bit about that as well. But remember, everything we've been talking about in those previous sessions, for example, the Earth isn't orientated with its axis perpendicular to the plane of the orbit. The axis is tilted at 23.5 degrees, so that some times of year the Sun is directly overhead at the southern tropic. At other times of year the Sun is overhead at the northern tropic. At some times of year the Sun is overhead at the equator. It varies through the year as the Earth rotates, being tilted on its axis like that. And just to give you a warm-up exercise, and to start you thinking about how you can relate things together from the different sessions that we're talking about, I have a quiz for you. I have an exercise that I'd like you to do. So here on my globe, here's where I'm based, here's where many of you are based, at Kiel in the United Kingdom, 53 degrees north of the equator. So here's my question. Think about the point at which the Sun is lowest on the horizon to our 53 degrees north position at the winter solstice, when the Earth's axis is tilted as far in the northern hemisphere, tilted as far away from the Sun as it is at any point in its orbit. At that stage, at the winter solstice, what elevation above the horizon does the Sun achieve when you're looking at it from Kiel? So in the middle of the day, in the winter solstice, from 53 degrees north, you look towards the Sun and you measure the angle of elevation of the Sun above the horizon. From what you already know about the Earth as a planet in space and the orientation, the geometry of the Earth, its axis, its orbit, you should be able to work that out. This 53 degrees north, how high does the Sun rise above the horizon at its highest point during the day on that winter solstice? When you've had a chance to think about that exercise and you've remembered that all the things we've talked about previously are going to become important again now, we're going to move on, and today we're going to talk about solar energy, Earth interior energy and gravity impacting on what's happening at the Earth's surface and affecting physical geography.